Hi friends, welcome back to a new session. In this session, we'll discuss effect of leakage flux on the operation of transformer. If you observe, in our previous discussion, we've just made ideal transformer means I don't have any, winding resistance should be equal to 0. But we had taken effect of winding resistance on the operation of transformer in our previous discussion. Similarly, ideally, I can say that the leakage flux is assumed to be 0. That means entire flux is confined to transformer core only. But practically, some flux will be there which leaks through air. Some leakage flux will be there. Leakage flux which links with flux which links with either low voltage winding or high voltage winding, but not both is called leakage flux. That's leakage flux will be there. So because of the leakage flux, what are the unwanted things we are going to have? So to overcome that, what we have to do, all those things we'll see here. Okay. So for explaining this topic, our previous session topic means transformer as a constant flux device topic is very important. Here we told whenever N1 I1 equals to N2 I2 means what? If you maintain primary MMF equal to secondary MMF. So at that time, I said that pi dash magnitude and pi 2 will be equal. Whenever their magnitudes are equal, they are all out of phase, they will cancel with each other. So core flux will be constant irrespective of your load change, like that I told. But practically, though you maintain primary MMF equal to secondary MMF like this, don't expect that 100% pi dash, 100% pi 2 will cancel. It will not. Because, see clearly, here if you take pi 2 dash, which is related to your primary, every flux will be having two components. One is mutual flux component pi 2 dash m. One is the leakage flux component pi L1. Similarly here pi 2 will be having two components. I can say pi 2m and pi L2. So if you want me to say percentage, how much percentage pi L1 is there? It's around 45% here. Sorry, 5% here. This is 95%. Similarly here 95%. Here 5%. So every flux will be having two components: mutual flux component, leakage flux component. 95% mutual flux component, 5% leakage flux component. Here also pi 2 will be having two components, pi 2m and pi L2. So pi 2m is 95%, pi L2 is 5%. Okay. If you maintain this condition, what is this condition? N1 I1 equals to N2 I2. N1 I1 equals to N2 I2. Don't expect the 100% pi 2 dash, 100% pi 2 will cancel. No, it will not. Only 95% of your mutual flux component of pi 2 dash and 95% of mutual flux component of pi 2 will cancel. But 5% leakage flux component pi L1 in primary side will be there, and pi L2 5% leakage flux component in secondary side pi L2 will be there. Because of that leakage flux in the primary, pi L1 will be getting some unwanted EMF. Because of this pi L2 in secondary, it will be getting unwanted EMF will come into picture. So what we have to do to overcome that, we'll see. Before that, let me write here. What is our heading here? Effect of leakage flux. Effect of leakage flux is our topic for this session. Effect of leakage flux on the operation of transformer. And the operation of transformer. So let me write here. By keeping primary MMF N1 I1 equals to N2 I2. By keeping N1 I1 equals to N2 I2 like this. N1 I1 equals to N2 I2. Practically 100% pi 2 dash, 100% pi 2 will not cancel. That's what I am writing here. By keeping N1 I1 equals to N2 I2, 100% pi 2 dash will not cancel. Otherwise 100% pi 2 will not cancel with 100% pi 2 dash. So then how much how much percentage only it will cancel means, by keeping primary MMF equal to secondary MMF, 100% pi 2 will not cancel with 100% pi 2 dash. It will not cancel exactly. Okay, can write here only 95 percentage of 95 percentage of 95 percentage of 90 percentage of mutual flux component of pi 2. What is that name? What is the mutual flux component of pi 2? I mean mutual flux component 95% mutual flux component of pi 2 means this pi 2m only. So 95 percentage of mutual flux component of pi 2, that is I can write pi 2m will cancel with 95 percentage of mutual flux component of pi 2 dash, that is pi 2 dash m. But 5% leakage flux component of pi 2. What is the leakage flux component of your pi 2? Pi L2. So I write that is pi L2 will not cancel with 5% leakage flux component of pi 2 dash, that is pi L1. That means what is the meaning for this? Clearly, observe clearly. Leakage flux means what? You tell me. In primary side, you are saying pi L1 is the leakage flux. Okay, in pi L2 is leakage flux. I told you by keeping this condition, you can cancel this pi dash m and pi 2m will cancel. But pi L1 will be there in primary side, pi L2 will be there in secondary side. Pi L1 means what? It is related to your primary winding. It links with only primary. Say example, it is coming like this. It will link with only primary winding. It is linking with only primary winding. Thereafter, it is taking path through the air. It is taking path through the air. Okay, it is taking path through the air. Okay. Now, similarly, in the secondary side also, so here pi L2, whatever it is there, it is linking with your pi L2 is a sub of pi 2. Pi 2 is because of your I2 current only. Whenever I2 current is like coming like this, your pi 2 is upwards. Similarly, pi L2 is also upwards. It is coming like this, and it is linking with only secondary winding. So it is not coming towards this side. This pi L1 is linking with only primary winding. It is not coming to secondary side. This pi L2 is linking with only secondary winding. It is not coming to primary side. That's why this pi L1 comma pi L2 can be called as a leakage flux, or you can say useless flux. What is the definition of leakage flux? Already we discussed in our last discussion. Flux which links with either LV or HV but not both is called leakage flux, or I can say flux which links with either primary winding or secondary winding but not both is called leakage flux. Yes, obviously pi L1 can be called leakage flux, pi L2 can be called leakage flux. So that only wrote here. But 5% leakage flux component of pi 2, that is pi L2, will not cancel with pi L1. Okay, because of this pi L1, I will be getting some useless EMF or unwanted EMF EX1 in primary side. Because of this pi L2 in secondary side, I will be getting some useless EMF or unwanted EMF in secondary. So that only let me write here. Because of pi L1, useless EMF EX1 is induced in primary side. Next, because of pi L2 leakage flux, useless EMF EX2 is induced in secondary side. Now tell me. So obviously, whatever we told is useless EMF EX1 in primary, EX2 in secondary, it should be compensated. Yes or no? Because that is useless flux. That is useless EMF because of useless flux. that should be compensated. How it should be compensated means you can write here these useless EMFs EX1 comma EX2 can be compensated. How we have to compensate it, that we'll see. Can be compensated by understanding following vector diagram. So here I need to explain some vector diagram. So before that, please note down this. Next I will go for vector diagram. So from that knowledge we can conclude how we have to compensate this EX1 comma EX2 in the primary and secondary sides respectively. Please note down. Yeah. Before explaining this vector diagram, I need some very basics which we already discussed in our previous discussion. So I need some basics from you. So please tell me. So try to remember this box. It will be useful for us in drawing this vector diagram. Okay. Tell me what is the angle between I mu and flux, which we already discussed. Okay, in our first sessions only we discussed I mu and pi, they are in phase 0 degrees. Angle between pi and E1 how much? According to Lenz's law, 90 degrees. Angle between pi and E2 how much? 90 degrees. Now similarly I am asking one more simple question here. You observe clearly and please tell me. Observe clearly, try to observe clearly here. This pi L1 is a sub of which flux? It comes under which flux? Pi 2 dash. This pi dash is because of which current here? Try to see this color and tell me. I use some different colors for making you to understand easily. This pi 2 dash is because of this I2 dash. So pi L1 is also because of I2 dash. So because of I2 dash, we are getting pi L1. So those will be in phase just like this case. Just like I mu and pi are in phase. Because of I2 dash only you are getting pi L1, they will be in phase. And one more condition. Suppose in this case, if you take this relation, if you neglect this I0 because the current is very less, in place of I2 dash, what I can write? I1. So simply I can write here from this I1 comma pi L1 I can write in phase. Why? Since I0 is negligible. If I neglect, I0 is negligible. I0 is neglected. Okay, very good. Next, tell me. Because of this pi L1, we are getting EX1 in the primary side. So pi L1 and EX1 are displaced by how much angle? 90 degrees. That means what? What is the meaning for this one? EX1 lacks Ex1 lags pi L1 by how much? 90 degrees. Tell me similarly, what is the angle with what is the your pi L2 is comes under which flux? Pi 2. Pi 2 is because of which current? I2. So pi L2 is also because of I2. So I can write here pi I2 angle between I2 and pi L2 is equal to how much? 0 degrees. Now angle between pi L2 and Ex2 how much? 90 degrees. What is the meaning for this? That is Ex2 lags pi L2 by 90 degrees. That's the meaning, right? This is the meaning. Okay, if you understand all these things, then it is very easy for us to draw a vector diagram here. Okay, you just generally tell me whatever the vector diagram you know with our previous knowledge. We'll take V1 as reference. V1 as reference. After 90 degrees, you know which current will come. Whenever voltage is connected, it will take some current, no? I mu. Why? To magnetize your transformer core. So that is what I can say, I mu. Because of I mu, you will be getting some flux pi. That is your pi. Because I already told here, I mu and pi are having 0 degrees displacement. Yes. Because of this pi, according to Lenz's law, E1 lags flux for 90 degrees. So I can write here, E1 lags flux by 90 degrees. If I assume it's a step-up transformer, if I assume it is a step-up transformer, if I assume it is a step-up transformer, you know, E2 will be greater than E1. So E2 is here. Now one more thing. You know already IW will be in phase with V1. That also you know. We already discussed it. IW will be in phase with the V1. We already discussed in our previous sessions. Okay. Now vector sum of IW and I mu gives you what? I naught. Okay. Here you have to understand some small thing. So otherwise it will be difficult for us to follow. Very simple thing here. Tell me, generally ideal case, in primary side you can write V1 bar equals to minus V1 bar. In secondary we write E2 bar equals to V2 bar. But here that means you know already if it is Z1, what about this vector? Minus C1, you know. Is that about minus C1? See, ideally you can take V1 bar equals to minus C1 bar, you can take here. Nothing wrong. And ideally you can take E2 bar equals to V2 bar also. There's also nothing wrong. But what is our topic? What is our topic here? Effect of leakage flux on the operation of a transformer is our topic. Because of leakage flux, pi L1, I got some unwanted EMF in the primary side. This should be compensated. That means V1 bar equals to minus C1 bar plus something is there here. That is very important. Similarly, in secondary side, E2 bar is equals to V2 bar is for ideal case, but practically plus something is there to compensate this EX2 in secondary side. Here something is there to compensate this EX1 in primary side. Therefore, V1 bar equals to minus C1 bar plus something. E2 bar equals to V2 bar plus something is there. So, please tell me now, you should not take this vector as V1. But you can take this vector as what? Minus C1. Because if it is Z1, this becomes minus C1. No doubt in that. And it is not E2 is equals to V2 should not write. So generally after E2 is induced in secondary winding, then only V2 load voltage will be there, no? So you can write your V2 lags E2 by an angle something. E2 lakhs V2 by an angle something is there. Okay. Up to here. Okay. And here people make a doubt. Sir, you told that I mu is making 90 degrees with V1. But here you drawn I mu 90 degrees with the minus C1. Similarly, IW in phase with the V1 you told, but here you drawn IW in phase with the minus C1. It's only approximation. There is no, I mean, we can, to be frank, really, yes, I mu should be 90 degrees with your V1 only. IW should be in phase with the V1 only. I can understand that. But here, just for simplicity purpose, just for making a vector diagram easy, I'm just drawing approximately. Instead of drawing I mu quadrature with V1, I just drawn I mu quadrature with minus C1. Okay. And I just drawn IW in phase with the minus C1 instead of drawing IW in phase with the V1. That's it. Okay. Now tell me. Now everybody, let me once again, let me draw a vector diagram for lag loads. Lag loads. Lag loads means you should understand one thing. I2 current lags load voltage V2. Okay, therefore this is what V2. So I2 lags V2. I2 lags V2. I2 lags V2 by an angle something. Once again. If I refer this I2 towards the primary, this becomes what? This becomes what? I2 dash. I2 dash. This becomes I2 dash. I2 dash. And if you want a resultant vector sum of I0 plus I dash gives you what? I1. So let me add to this I0, let me add I2 dash, or to this I dash, let me add I0 for getting resultant vector. What is that? I1. This is what I can say, I1 vector, I1 vector. Now let us include all those things, whatever we discussed here. First one, what is the angle between I1 and pi L1? What is the angle between I1 and pi L1? 0 degrees. That means your pi L1 should be in phase with I1. Very good. Next, what is the angle between pi L1 and EX1? 90 degrees. That means EX1 lags pi L1 by 90 degrees. So this is what your pi L1. Lagging. So lag means after pi L1 only your EX1 will come. EX1 will come. EX1. How much angle between pi L1 and EX1? 90 degrees. Lagging. Therefore, let me show symbol minus. How much angle? 90 degrees. Minus J. So EX1 lags. Lags is there. That's why I'm just writing here minus. How much angle? 90 degrees. That's why I'm writing minus J. And we have to show that a drop because of leakage flux. We are having some, because of leakage flux, we are getting some EMF is induced. That EMF we have to show in terms of, it is in primary side, minus JI1 bar. You have to use here X1 or R1. X1 you have to use. Because of something, if you are having only drop, you have to show that drop with the reactive element. Because of something, if you are having a drop is there as well as loss also there, you have to show that drop with the resistor parameter. But here, because of leakage flux, you will be having only drop, not losses. That's why I'm just showing a reactive element minus J I1 X1, right? Now, once again, because of this one, let me indicate this one also. Now tell me your pi L2 and pi I2, they are in phase. Therefore, wherever pi I2 is there, let me write pi L2 in phase with I2. Whenever pi L2 is just shown, now pi L2 and EX2, that is how much angle? 90 degrees. That means what? Your EX2 lags pi L2 by 90 degrees. That means this is what I can say: EX2 lags pi L2 by 90 degrees. That means what I have written here, minus lagging, therefore you have to use minus symbol, minus how much angle? 90 degrees. Minus J it is in the secondary side. So I2 bar, X2 bar, X2 bar. Now, please let me conclude now. So, as I told you, this is a useless EMF in a primary side. I already explained here. Useless EMF in a primary side. This should be compensated in primary side. Primary side means if you want result vector V1 minus E1 bar plus something is there here. Plus something is there. What is something? This something is nothing but to compensate what? To compensate EX1, and this something nothing but to compensate EX2. If you want to compensate EX in primary side, what you have to do? Say how much magnitude is there? Same magnitude if you induce in out of phase. If you induce out of phase like this, you should be having 180. 180 degree should be there between this vector and this vector. Okay, like this. Okay, same magnitude. Therefore, same magnitude. This is indication of same magnitude. These two vectors are, they are this way out of phase. 180 degrees difference is there. Therefore, minus becomes plus here. J I1 bar X1 bar X1 minus J I1 X1. So that gives you resultant V1 in primary side. So now tell me what it should be here. V1 bar equals to minus E1 bar plus J1 X1 in primary side. Similarly, in secondary side, is not E2 equal to V2. E2 equal to V2 plus something is there. This is what I can say V2. To this V2 plus something I have to add. How much? What I have to add here? How much unwanted EMF, useless EMF is there in secondary side EX2? Same magnitude you have to induce out of phase. That means to this V2 vector you have to add same magnitude out of phase. It is like this. So out of phase means it should be like this. It should displace how much angle? 180 degrees. So same magnitude. Since it is only displaced 180 degrees, minus becomes J here. I2 bar X2. So that becomes your E2. So now E2 bar equals to V2 bar plus what? E2 bar is equals to V2 bar plus what? Ji2 X2, Ji2 bar X2, Ji1 bar X1 here. Okay. So this is nothing but what? Ji1 X1 is nothing but to compensate EX1. Ji2 X1 is nothing but to compensate EX2. Okay. First, draw this vector diagram. This is IW. Right. So I think you understood this vector diagram. Next, Tell me here, in this case. Yeah. What is the nomenclature for this X1? We can give X1. X1 is nothing but primary leakage reactance. What is that? Primary leakage reactance. We are placing in the primary side. Why? To compensate this EX1. So I can give nomenclature for this X1 as primary leakage reactance, primary leakage reactance, primary leakage reactance, primary leakage reactance required to compensate EX1 in which side? In the primary side. Tell me what is the value of that X1. I can say X1. How can you calculate value of X1? Very simple. Because we already told this this magnitude and this magnitude is same. That means mod EX1 should be equal to mod I1X1. Yes or no? If you have to induce here for to this EX1, I have to induce out of phase vector, then only I can compensate that EX1, right? So mod EX1 should be equal to I1 mod I1X1. From this X1 is equals to mod EX1 divided by I1. So this is the name. What is the name? I had given here. So primary leakage reactance required to compensate EX2 in primary side. Similarly, X2 means what? Secondary leakage reactance required to compensate what? EX2 in secondary side. How much? I already told you this magnitude, okay, and this magnitude should be equal, this and this, okay. So mod here mod EX2 should be equal to mod I2 X2. So X2 is equals to mod EX2 divided by I2. Okay. First note on this. This much, I think completed. Huh? Next. If you observe clearly now, people, they will be having some confusion like this. You can write as a note here. People will think like this. So primary winding, suppose if a conductor if it is having twisting movement, so further some inductive nature will be there. Inductive reactance will be there in your primary winding. That is physical inductive reactance. It will be there in the primary winding, it will be there in secondary winding. But here what I am saying is physical inductance reactances will be there in primary winding and secondary winding. That is okay. In primary side and secondary side, okay. In addition to that, an imaginary or fictitious reactances we have to place in the primary side and secondary side to compensate EX1 and EX2. That means you have to place X1 and X2 in the primary and secondary side to compensate EX1 and EX2. This X1, X2 can be called as imaginary or fictitious reactances which are placing in the primary and secondary side. In addition to physical inductance reactance, already physical inductance reactance already it will be there. It's okay. But if you see maximum questions, whatever they will mention here reactance, you should take that reactance as leakage reactance only. problematic point of view also. Okay, so let me note here. physical 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 inductance reactances exists in primary side and secondary side, full stop. In addition to this, imaginary or fictitious reactances, x1 comma x2 should be placed in primary side and secondary side. Why? To compensate. Why you are placing x1? To compensate ex1. And ex2 respectively. x1 is used to compensate ex1 in primary side, and x2 is placed in secondary side to compensate ex2. It's okay. Okay, that means what? Your diagram will be like this. This is what transformer having a primary winding and a secondary winding like this. Previously we discussed effect of winding resistance. Now we are showing effect of leakage reactance, effect of leakage flux. So let me show that leakage reactance here in primary side as x1, and here I can show x2 like this. This is what supply voltage V1 bar, load as usual E1, here E2, and here number of turns N1, number of turns N2. This is what direction of your core flux. This is equivalent circuit of figure of transformer after including effect of leakage flux. Leakage flux will be there. Because of leakage flux, a useless EMF will come. To compensate that useless EMF, you have to place x1 in the primary side. x1 can be called as the primary leakage reactance. x2 can be called as the secondary leakage reactance. Nomenclature is very, very important. I told x1 leakage reactance, primary leakage reactance. I told x2 as a secondary leakage reactance. Whereas in our previous discussion, I just showed some shunt branch parameter x0. That x0 means what? Magnetic reactance. This one means what? Leakage reactance. There, through that x0 current IMU is flowing. IMU was flowing. Previous discussion. That IMU is used to magnetic transformer core. That's why you can call x0 as a magnetic reactance. Here, why just place x1 here? To compensate EMF, unwanted EMF, which is due to leakage flux. That's why x1 can be called as primary leakage reactance. x2 can be called as secondary leakage reactance. Okay. Load voltage V I can show. Okay. This thing. And here, first note on this. Next we'll go for referring leakage reactances. Right. Here, we have to follow one condition for referring your reactances from one side to other side. Previously, for transferring resistances from one side to other side, we followed one condition. What is that? Copper loss in the resistor before transfer is equal to copper losses in the same resistor after transfer. That is the condition we just studied. So we just followed for getting R2 dash formula and R1 dash formula. Here we have to follow one condition for for knowing the formula of x2 dash and x1 dash. While transferring reactances from one side to another side, you have to follow one condition. What is that? Per unit reactance drop before transfer should be equal to per unit reactance drop after transfer. This is the condition you have to follow for transferring reactances. Now tell me, secondary to primary. That means if I refer secondary reactance x2 towards the primary, x2 becomes x2 dash. I need that formula. For that, what you have to do? Tell me per unit reactance drop before transfer. Before transfer, this x2 is secondary because secondary to primary I'm just going, right? Secondary to primary I'm coming. Before transferring, x2 is in secondary only. Tell me per unit reactance drop in x2 if it is in secondary. Actual reactance drop I2 x2 by base value E2. Already we told this formula in referring of your resistances, and before that also effect of winding resistance. There also we discussed this topic, per unit resistance drop. Similar here also per unit reactance drop. That's the only difference, right? So secondary to primary. Before referring x2 in secondary, per unit reactance drop in x2 is nothing but I2 x2 by E2 is equal to, if I refer this x2 towards primary, it becomes x2 dash. What is the current flowing in primary? You can indicate here. This is the current in primary side I1. The current in secondary I2. So current after referring x2 towards the primary, it becomes x2 dash I1 x2 dash by E1. Tell me from this x2 dash equals what is the formula? x2 into I2 by I1 into E1 by E2. Tell me x2. I2 by I1 means what? 1 by k. E1 by E2 means what? 1 by k. Therefore, x2 dash is equals to what is the formula? x2 by k square is the formula. Tell me similarly, I need a primary to secondary. That means if I refer primary leakage reactance x1 towards secondary, you have to follow this condition. Per unit reactance drop in x1 if it is in the primary side. What is that formula? I1 x1 divided by base value E1 is equal to, if I refer this x1 towards secondary, it becomes x1 dash current in secondary I2 by I2 x1 dash by E2. Tell me from this what might be the formula for x1 dash is equals to x1 into I1 by I2 into E2 by E1 is equals to x1 into I1 by I2 means k. What about E2 by E1 means k. So I can write x1 into k square is the formula. So x2 is equals to x2 by k square. x1 dash is equals to x1 into k square. Now tell me I'm asking this question. Total leakage reactance refer to primary side. Refer to primary side. Refer to primary side means what? See, actually, previously we remember this figure, right? So let me draw once again for the understanding point of view. I1, X1, X2, I2, these things I'm asking. Core flux pi, right? This is what I can show E1 and this is what I can show E2. I'm asking if it is primary, if it is X1 is in primary, that can be called as primary leakage reactance. X2 is in secondary, that can be called as secondary leakage reactance. Already I had given that. But I'm asking now, total leakage reactance referred to primary side. Means referred to primary means what? Referred to primary means we are referring secondary parameters towards primary. That's the meaning. So already in primary, X1 is there. In addition to that, if X2 is coming this side, it becomes X2 dash. So this total becomes X01. X01. Similarly, I need a total leakage reactance refer to secondary side. Refer to secondary side means what? If I refer to secondary means already in secondary X2 is there. If you refer primary side X1 towards secondary, there is a meaning. In secondary already X2 is there, plus from primary if X1 is coming towards secondary, it becomes X1 dash. That gives you X02. So you just remember this one also. Total reactance referred to primary side X01. Total reactance referred to secondary side X02. And X21 formula already given. X2 by K square, where K equal to what I had given. K equals to E2 by E1, N2 by N1, I1 by I2. X1 dash equals to X1 into K square, where K equal once again E2 by E1, N2 by N1, I1 by I2. Okay. So this is effect of leakage flux on the operation of transformer and referring leakage reactances. If I refer, X2 becomes X2 dash, X1 becomes X1 dash, these formulas, and total leakage reactance referred to primary side, total leakage reactance referred to secondary side. Okay. This node.